Hi everyone, I am Biresaw, a PhD student in food engineering and biotechnology at the University of Bolzano under supervision of Professor Paolo Lugli. I'm here today to present our work, which is laser-fabricated flexible nanographene-based capacitive sensor to detect the pH from saliva. During this presentation, I will give you a short introduction, and then I will show you sensor fabrication process as a methodology, and finally I will discuss the results what we achieved during this work. Saliva is a complex medium secreted inside the mouth from major salivary glands, which are parotoids, sublingual, and submandibular. These major salivary glands are distributed in different positions inside our mouth. Saliva becomes the most preferable diagnostic specimen compared to other specimens like blood, due to its possibility to collect it in a non-invasive and non-stress way, and also it's possible to collect it frequently and in a rapid way. Nowadays, saliva becomes used to identify different diseases like diabetes, inflammation, infections, and hormonal perturbations or disorders. In particular, the pH of saliva is a very good indicator of the gingivitis, tooth decays, and anxiety disorders. In general, pH of saliva is a good indicator of the health condition of a mouth. pH is a quantitative measure of the acidity or basicity for liquid solutions, and it's also a negative logarithmic measure of the hydrogen ion concentration. So the pH value of a saliva for a healthy person ranges from 7 to 7.3 in the scale range. So salivary pH is one of the indicators of the dental health of a person. So if the pH of a human being or a person falls below 7, it's better to check personal doctor, because there may be some mouth dental problem inside the mouth. So as a sensor fabrication process, we use a polyimide substrate, which is a Kapton substrate, because it is disposable and flexible. And to fabricate the electrode, we use carbon dioxide laser using 6 watt power and 15 centimeter per second as speed. We choose carbon dioxide laser to fabricate our electrode because carbon dioxide laser fabrication process or printing process is a novel technology to fabricate conductive films, and also it's easy to use or to fabricate electrodes. After fabricating the electrodes, we paint silver ink on sides of the electrode to have a good contact during measuring the sensor. And during painting this silver, we use manual painting using a brush, because we don't. If we use another squeege like screen printing, we may damage the spongy nature of the laser-induced carbon electrode. So we prefer to use a manual printing. After printing, the electrode was annealed in oven at 120 degrees centigrade for 15 minutes. This is used to remove the solvent from the silver ink, and also it's used to have a better contact between the silver ink and the electrode itself. And then we prepare graphene oxide, which is 4 milligram per milliliter solution, and drop cast in between those electrodes, and we smoothly distribute to have a uniform distribution between these electrodes. So we choose graphene oxide as a sensing element due to its a high surface area to volume ratio, and also due to its zero or quasi band gap. So due to this, it is used as a sensing layer in different devices. And that's why we choose graphene oxide as a sensing layer during fabrication of our sensor. And this is the final sensor that we developed in our sensor in our lab. And after fabrication of the electrode, what we did is we measured cyclic voltammetry for each individual different pH solutions or pH buffer solutions. Then after measuring the cyclic voltammetry, we calculated the area under the curve of the cyclic voltammetry for each individual pH solutions. And then using this area under the curve of cyclic voltammetry, we convert to specific capacitance using this formula, which is the area under the curve divided by mass of the graphene oxide times the scan rate during cyclic voltammetry times the potential window for cyclic voltammetry. So first we measure cyclic voltammetry, then we calculate area under the curve, and finally we got the specific capacitance. And after having the capacitance for each individual pH solution, we draw a linear correlation between the different pH solutions and the specific capacitance that we calculated from the area of the cyclic voltammetry. As you can see here, the correlation is it's very correlated with the correlation coefficient of 0.98 and with the equation as shown here. And also you can see this one is the real saliva sample, which is allied between normal or buffer pH solutions, which is our sensor is a very good sensor even to measure the saliva, the pH of real saliva. As you can see from the previous graph and from this graph, when we increase the pH from lower to higher, then the specific capacitance becomes lower and lower. This is due to this, the acidity or the H plus ion modifies the fringe electric fields which are generated by the electrodes, and this leading to the change in permittivity. This is due to permittivity. So it's the capacitance, which is the permittivity is a measure of the resistance of the electric field. So the change in permittivity also alters or affects the final capacitance value. That is why the capacitance value becomes lower and lower. And finally, we, after preparing different pH solutions or pH buffer solutions, we, to get the actual pH value, we use the pH meter to measure this pH value. And finally, we compare this measurement with our own developed pH sensor. As you can see, the values are very comparable here with the pH sensor, the normal commercial pH sensor. And to see the precision of our sensor, we calculate the error between the commercial pH meter and our sensor. As you can see here, the percentage error is below on 10, which is around 8, the maximum is 8. So the biosensor, the sensor that we developed is comparable with a pH meter, with a commercial pH meter, and we can use to measure the pH of saliva. In conclusion, we demonstrated the use of graphene oxide as a sensing layer due to its high surface area to volume ratio and due to its zero or quasi band gap as a sensing layer on a capacitive saliva pH sensor, which we developed with laser-induced graphene electrodes. And the sensor was used to measure, or the range of the measurement range of our pH sensor is from 3.83 to 8.18, which was characterized by cyclic voltammetry. And finally, the sensor we developed is really comparable to the commercial pH meter because the error is less than 10%. And this pH sensor can be used as cost-effective dental health monitoring system by measuring the pH of saliva. These are some references that I used in my presentation. So I would like to thank you. I would like to thank you for attending my presentation. Thank you very much.